show how length contraction can falls out of the Lorentz equations that we derived in the last video. So let's start here. I place a 1 meter ruler in the x primed axis of k primed. Okay, so we can think again of the k primed system as being the train. Think of me as being on the train holding my 1 meter ruler as measured by me along my x primed axis. So I place a 1 meter ruler in the x primed axis of k primed in such a manner that one end, so the beginning of the ruler, let's say, coincides with the point x primed equals 0, whilst the other end coincides with the point x primed equals 1. Okay, so we're just saying this here. So if this is our k primed system, we have t primed on this axis, x primed here. This red line represents the 1 meter ruler. Okay, so one end is at the point x primed equals 0, the other end is at the point x primed equals 1. And so what we want to ask is, what do these 2 points correspond to in the k system? So our ruler will look like this in the k system. I think actually I should have probably shifted this red line up a little bit, because these t here won't be the same as t primed, but that doesn't matter too much. So really we want to know what L is here. What is the length of this ruler in the k prime system? What is the length of my ruler that I'm holding in the train as I fly past you? What do you measure that ruler to be? And so, so that's what I've got written here. What is the length of the 1 meter ruler relative to the system K? So what do you measure my ruler to be as I fly past you on the train holding my ruler out? So, in order to learn this, we need only ask where the beginning of the ruler and the end of the ruler lie with respect to k at a particular time t of the system k. So let's just choose t equals 0 again, because t equals 0 is easy. So it doesn't matter what time. Again, we're just taking, you are on the platform and you're just taking a snapshot at any time as I fly past on the train. So that's why we can just choose any time here. And we'll show later that it works for any time. Okay, so that's why I've just labelled here this point on this t-axis, where this ruler meets the t-axis, is t equals 0. So let's just write down our Lorentz equation for the x primed axis that we found in the last video. So that's x primed equals x minus v times t divided by the square root term on the bottom. So now, for the point x primed equals 0, so again, the start of our ruler here, for that point, so we'll have x primed here is going to be equal to 0. We said we're going to set t equal to 0, because you're just taking your snapshot when your time equals 0. But this t could be anything, and we'll show that later. So we set t equal to 0 as well, so we get x minus 0 divided by all of this. We can see that that's going to come out as x equals 0, because if we multiply both sides of this equation by the square root term on the bottom, we'll get 0 times this square root term, which is just 0, and we'll just be left with x on this side, so we'll just have x equals 0. So x primed equals 0 corresponds to x equals 0 in our k system, just like we have written here. Okay, so So now we also want to ask, what do we get for the point x primed equals 1? Because remember we had our ruler here. At the beginning of the ruler was at 0, the end of the ruler was at the point x primed equals 1. So let's plug in, well, let's keep that Lorentz equation there so you can see it. So let's just plug in x primed equals 1. So we have a 1 here. Again, t is still 0. We're still taking our snapshot at your time 0. So we just have x minus 0 again on this square root term. And we can multiply both sides by this square root term. So we'll have 1 times that on this side and just x on this side. So x will be equal to the square root of 1 minus v squared on c squared. Okay, so that this x here is then representing our length L here. Okay, so we've just showed how length contraction falls out of this Lorentz equation. Yeah. So the 1 meter ruler in my system, as I zoom past you holding it out and you take a snapshot, you measure it to be this distance here, which is going to be less than 1 meter. So as I said, let's do it for an arbitrary length, delta x primed, and an arbitrary time t. So let's just choose any arbitrary length instead of nice easy 1 meter, and any arbitrary time instead of the nice easy time equals 0. So in this case, this is the little diagrams we have. So our k prime system, the train, here's another ruler that is at length L naught, so any arbitrary length. And you'll notice I shifted the times this time to make that, because that's how it's going to be. This time t isn't going to be the same as this time t primed. So now we have that same ruler as measured from your perspective on the platform is going to be this length L. So its endpoints are going to be at L1 and L2, whereas the endpoints in my frame are at 0 and L0. And this, you're going to take your snapshot at time t0 this time, just some arbitrary time. So let's see what happens. Let's just write down the Lorentz equation again. Which is this. Now, we plug in again our x primed equals 0, because that was one end of our ruler over here. So we get 0. Our x, that end, this start end of our ruler, in the k primes, corresponds to L1 in this k system. So this x will be L1, because this, you can think of this as the beginning of the ruler, this end is the beginning of the ruler, minus v, this time times t0, because we're not starting at t equals 0. You're not taking your snapshot at t equals 0, you're just taking it some arbitrary time t0, again divided by this square root term. And so we can multiply both sides by this square root term, so you just get 0 on this side. You'll end up with 0 equals L1 minus v times t0. And so we can move the v times t0 over this side, and we'll just have L1 is equal to v times t0. Okay, that's what we've got for our point L1 then. So then we plug in the other end of our ruler, the point that corresponds to the other end of our ruler in x prime, which was L0. So x prime is going to be L0. That end of the ruler corresponds to this end of the ruler, L2, in our k system. So this x will become L2. still have minus v times t naught, because we're still taking a snapshot at t naught, again divided by the square root term. And so from that, if we look, so here we've got it written here, since L2 minus L1 equals L, well, let's hide that for a second, actually. So what I've done here, same thing, got L2, but now we've got minus L1. So that's because we found over here that L1 is equal to V times T naught. So we have V times T naught here, we can just substitute in L1. Now since L2 minus L1 is equal to L, so this length here, L2, minus this length L1, is the distance between L1 and L2, which is the distance, the length of our ruler, which we just said was L. Right? So here we have L2 minus L1. Since that equals L, we can just put in L here. So we'll have L naught equals L divided by the square root of 1 minus v squared on c squared. So we could multiply both sides by the square root term again to get L equals L naught times the square root of 1 minus v squared on c squared. And this is the same as L naught divided by gamma, where gamma is the Lorentz factor. So 1 divided by the square root term. And I think that looks exactly like the equation that you've been using in your classes. And so I won't do, in the interest of keeping this video shorter, I won't do the same for time dilation. But in the case of time dilation, I'll just bring back that equation we found in the last video. So in this case, you're thinking about a tick of a clock, say. So your t naught will go from 0 to, say, 1, if you're just thinking about one tick. So 1 second, perhaps, you could think of it as. And you want to do exactly pretty much the same thing we just did with the x coordinate, but with the t prime coordinate. So that tick of the clock can occur at any point in space. So again, this x can be arbitrary, or you could just set it to 0 to simplify this term, to get rid of all of that. And then you want to find out what your t is in terms of the two points, say t primed equals 0 and t primed equals 1, and see what you end up with.